Now let's work another example where we are determining the pH of a weak acid. We are still going to use we're going to use hydrofluoric acid, but this time it's a much lower concentration, 0.05 molar. So this is going to be an example where the approximation doesn't work, and we're going to go through that. All right, so I have my HF breaking into H plus and F minus. I write my Ka expression, and I've looked up my Ka value for HF, and I'm going to set up my ICE table. 0.05 for the initial, and then I have 0 and 0, so minus X plus X plus X, and I get my equilibrium expressions. And then I plug them into my constant expression, and I'm going to try the approximation by neglecting the subtracted X, and I get a simplified equation, and I'm going to multiply both sides by 0.05 and get x squared equals 3.55 times 10 to the negative 5, and if I take the square root, I get x is equal to 0.005958, and if I check the approximation by taking x over the original concentration, I get 12%. So the approximation is not okay, but the math is so fast here, all I did was multiply Ka and the concentration and take the square root and then check the percentage. That is much faster than using the quadratic. A lot of times students think, why learn this if it doesn't always work? Well, it works in most situations, and again, the math should become so fast for you that it's a quick check to avoid the quadratic. All right, so let's go ahead and solve this using the quadratic since the approximation didn't work. So we have our ICE table set up. We're going back to the original expression, and so we have to multiply both sides by the 0.05 minus X. And we get this, and we need to distribute the number and then combine all the terms, move them to one side, set equal to 0. So we get our A equal to 1, our B is 7.1 times 10 to the negative 4, and our C is negative 0.0000355. Go plug it into a quadratic equation solver. I just find one online and plug in A, B, and C, or some calculators are also able to do that, and I get my two X values. And in this case, when we're looking at what X is representing, a negative value is not going to make sense. So we know that this is our correct X. And at this point, you've done a lot of math. You may need to reread the question. And we are trying to find the pH. So pH is equal to the negative log of H plus, which is related to X. So we plug in to find pH. pH is equal to the negative log of the X concentration, because X is representing H plus, and we get a pH of 2.251.